Yeah. Okay. So remember we talked about this. Yeah. So here's the summary of our last class. So we have found several interesting patterns, right, for the partitions. And so first we had this line PON, right? So what was PON? It was just the total number of integer partitions of n, right? So it's a number of ways to decompose n as a sum of positive integers. And you see it grows kind of like this, right? It grows pretty fast. So at some point we'll study what happens when n is very large. So how fast it grows for large n. But for now, just think of it as an integer sequence. Like this 1, 2, 3, 5. At this point, it goes like Fibonacci sequence, right? But then it breaks down. Instead of 8, you get 7, and so on. Yeah. So okay, we'll talk about this later. So like, is there any relationship with Fibonacci sequence? Anyhow, and then we saw that so there are two dualities, right? There are two correspondences between the number of odd partitions and number of distinct partitions. So odd means every single part is odd, and distinct means that all parts are different, right? And the second correspondence was between symmetric, so those which are invariant under the flip under the diagonal, and odd and distinct partitions. So and then at home, apparently, so that's what we did last time. There's a beautiful picture here. Just essentially, you can explain it to to an not undergrad, to elementary school student, right, or even to the K student, right? So just try to describe it in terms of matching parts. It's going to be some complicated formula, maybe not that complicated, but the picture is worth 1,000 words here. Okay. And then how about this one? So who wants to explain us? So then there's this story about divisibility by 3. So we looked at partitions whose parts are not divisible by 3, all of them, and then map them against those with partitions of n, and each part is not repeated 3 or more times. Who wants to explain this story? I saw homework by Emily. Like yesterday I checked, so she looked at some examples. So Emily, do you wanna go? Do you wanna explain?
Yeah, sure. I'm not sure if I did it correctly, but what I did was I listed all of the partitions of 11, and I essentially went through every single step, and I found all of the ones that weren't divisible by 3 and then not repeated 3 or more times, and I found that they're the same number.
Good. So can you give us a list? So we're just gonna put them in here, or in fact,
share my
yeah, that'll probably be better. Okay, so because okay, and did you come up with a map with the correspondence, like with the rule which would prove it for? So example works, but we need the proof. Right?
I didn't get to the proof.
Okay, that's right. That's so. Just before you go, let me remind you one more part of the last week's lecture. So remember, we talked about this odd, odd versus distinct, right? Now, here's a quick question. So, what does odd mean, right? So odd means that the number is not divisible by 2, right? That's another way to say what odd is. Okay, so that's simple enough. Now, what does distinct mean? Distinct means that a part is not repeated more than 1 time. Does it sound familiar? So not divisible by 2 and not repeated more than 1 time. And then you roll back to here. Not divisible by 3, not repeated more than 3 times. Okay, not repeat yet. Sorry. So distinct means not repeated 2 times or more. So not repeated more than 1 time. Or so in this language, it's not repeated 2 times or more. And now compare it to this. So divisibility by 3, and then divisibility by 4, and then divisibility by any. I should probably put k here, but anyhow, divisibility by k. So and just to refresh your memory, I want you to show this slide, right? So that was the matching between. Yes, Eunice, please go ahead.
I just wanted to ask, like, what do you mean by part? Like, what is a part?
So here, 4, 3, 2, 4 is a part, 3 is a part, 2 is a part. So part is a it's a part of this. So partition is a way to decompose numbers into parts, right? So for example, this partition has 3 parts: 4, 3, 2. So remember, we talked about this distinct versus odd, right? So here, in this column, all parts are distinct, right? 5 is not equal to 1, 4 is not equal to 2, etc. So every part is different. And here, every part is odd, right? And then, as you can see, some of them are odd and distinct at the same time. And then the corresponding. So if it's the case, we just map them next to each other. And those parts which repeat themselves, we use this binaries decomposition, right? So we would say to go from distinct to odd. Yes, what's the question?
I'm sorry. But like you say that when we are trying to proving the number of odd partitions and distinct partitions are same, we use binary representation.
Okay.
So can we use ternary representation to prove the
Good.
number
So, excellent suggestion. Did you try this at home?
I also find that the divisibility of 3, there's some connections between the divisibility of 3 and the repetition for 3 or more times, they're the same. And I consider the ternary representation, but I have not done it.
Okay, good. So let's do it right now. So I'm gonna let Emily share. Actually, Emily, can you share the screen? So I don't think I can give you privileges, like the way my account is set. Can you try to share screen?
Let me see if it lets me. Yes, it will let me. Okay, one second.
Okay. So we can look at your screen and then see if this suggestion by Eunice would work.
Can everyone see it?
Yeah, so we see this, right? So okay, so not in green we have not repeated 3 or more times,
and then I put like ND for not divisible, and then I counted each one and they were equal.
Mm-hmm. Okay, so maybe can you maybe make the make a table like we did in, so how many? Okay, 29 for both sides, right? So probably I think it will be a bit longer for so maybe, so is it 11 is the only one that you did, or did you do a smaller number maybe?
And then I also tried it with like not divisible by 4 and not repeated 4 more times, but I still did it with a partition of 11.
Oh well, and then so how many you got in each?
I got 39.
39, yeah, that's pretty good. So let's do together maybe smaller numbers. So I think I was
okay.
I think I started with we can maybe, and then we'll come back to this thing. So and then we'll sort of make 2 columns. Good. So could you get back from sharing? Yeah. So great. So and then I'm glad that you guys found a lot of similarities, right? So Mathematica. Did you get Mathematica if you need it, guys? I hope it's right. So. Don't worry, this is just an unrelated calculation. Okay, so let's check on the 7 integer partitions. Okay, let's start with 7, right? So let's first start with not divisible by 3. Okay, so which partitions, you can just shout, you can just say, so which partitions are not divisible by, so which partitions are not divisible by 3, so and then those which are divisible we're going to remove, right? So 7 is okay, right? So then 6, 1, 6 is divisible by 3, so we delete it. 5, 2, not divisible by 3. 5, 1, 1 works. 4, 3, remove it. 4, 2, 1 is okay, right? So 3's go this way. 3, 2, 2. So this is divisible, and the rest looks okay, right? Do you agree? Okay, and then sort of parts repeat. Parts do not repeat 3 or more times. Okay, so 7 is so 7 is okay, 6, 1 is okay. So 5, 1, 1 was already oh no, repeat, excuse me, yes, so it's fine. 5, 1, 1 is okay. Now this is okay, okay, okay. So now 4, 1, 1, 1, it repeats 3 times, right? So 3, 3, 1, that's okay. This is still okay. And all these guys looks like we need to remove them, right? Because they have repetition of 3 or more times, right? Okay, so how many do we have? 9 here. 9 there, so that's the same number. Okay, so now let's try to make a correspondence, right? So I'm gonna put them together next to each other. Okay, so now let's play this game. So you can annotate, or you can maybe send in chat or whatever. How do you think the correspondence should go? So given this idea about base of 3 in mind, which partition should be mapped to which partition? Right, so Kyle is making maps.
So what I'm doing for the parts that don't repeat 3 or more times, like if they are divisible by 3, if there's a part that's divisible by 3, you just divide it by 3.
Mm-hmm. Yes.
So for instance, 6, 1 goes to 2, 2, 2, and 1.
Mm-hmm. Yeah, so 7 is 7. Yeah, those which are neither, I mean, you can just map them to each other. There's also 5, 2, right? So 5, 2 should go to 5, 2. And 5, 1, 1 goes to 5, 1, 1. Excellent. How about 6, 1? Yeah, 6, 1 is 2, 2, 2, 1. Yeah, that's right. Good. So you see, it's the same idea, right? So then, again, so let's summarize what Kyle just said. So, for example, why is this 1, 1, 1, 1? Right? Corresponds to this one, 3, 3, 1. What is the rule, right? Or in the other way, right? Or excuse me. One more up. Annotation gets shifted like this. Good. So it's you can formulate sort of this dictionary either way, right? So from right to left, as Kyle said, you just divide by 3, right? So if so the first group of numbers, first group of partitions, they're not divisible by 3, right? And in the second one, they don't repeat itself more than 2 times. So whenever we have number 3 in the second group of partitions, we just divide it by 3, and we divide until it divides. So here we have, well, what kind of powers of 3 we have? We only have 3s, but if you go to 9 and higher, there'll be 9s. And I think if you look at Emily's list, she has more, right? So We can get to Emily's list after we're done with this. Maybe it will be quicker to do the mapping, right? So there's a 3, 3, 1, so you just divide by 3 and you get 7 ones, right? And if you want to go backwards, so how would we do it back? So we do the trinary representation, right? So we would combine them in groups of 3 like this, right? So that's 3, 3, and 1. So here, this gives you 3, and it gives you 3, 2, 2. Right. So yeah. So this is the representation in terms of base of 3. Questions? So see, it's very easy. It's like once we put the previous exercise into perspective, this one is a piece of cake. So and now you can imagine you can do the same for other bases. You can do base 4, you can do base 5, you can do any base. Right? It doesn't have to be prime, right? It's true for any. So in fact, using this example, let's do maybe divisibility by 4. We'll also take 7, right? So take these numbers, right? And then first we do not divisible by 4, right? So which of them are not divisible by 4? So these 4 aren't. So this is divisible. Take this out, and that's it, right? So okay, and then when those where parts do not repeat 4 or more times. So we get was the first one with 4. So this one. So this one goes, and these two. Right. So do we have a match? 12 guys here. 12 guys there. Okay, so now let's do the mapping. Okay, let's do the exercise again. So can you annotate? So now we're matching those parts which are not divisible by 4 versus partitions with parts do not repeat 4 more times. Right, so 4, 1, 1 goes to, so just take it like this, right? So it's 4 plus 1, 1, 1. Here there's also 4 to 1. Right, and then there's a bunch of partitions which you cannot do anything about it, right? So it looks like the rest are because of this one. So here you can also do 4. Yes, there are 4 ones, and that's it. And others they just go to themselves, right? So 7 goes to 7, 6, 1 goes to 6, 1, 5, 2 goes to 5, 2, 5, 1, 1, 3, 3, 1, 3, 2, 2, right? All of those partitions are they're presented both in both lists. Yeah, that's exactly right. So you see, the only 3 non-trivial correspondences here. Yeah. Good. So now you see that there are infinitely many. Okay, I mean, not as many correspondences as the length of the partition, right? So then you can do not divisible by 5, not divisible by repeat not more than 5 times, etc., etc. Right. So again, it doesn't have to be a prime number. It's just a matter of decomposing as powers of that number. Okay, so see, it actually sounds pretty cool, right? So like there's like a whole family of dualities in the sets of integer partitions. Okay. Any questions? Yes, Emily.
Quick question. For Mathematica, I was trying to use it for like listing the partitions and I downloaded it and everything. But when I like type in integer partitions of 7 or whatever, it doesn't list them like it does on yours.
You need to you press Shift Enter instead of Enter.
You're supposed to press Shift Enter.
Shift Enter, yeah. So I do it like this with the fingers. Boom.
Okay.
Yes, it's good.
I kept trying. I was trying for like an hour to figure it out.
Oh, I'm sorry. Yes, it's probably not written anywhere.
Okay.
You know, it's one of those jokes when like, you know, you're doing a lab, say in physics, and then like, you know, you forgot to plug in the
That one thing.
those, yeah, and you're scratching your head. Why is it not working? Yeah, so you hold Shift and then hit Enter.
Okay.
That's how evaluation works. I think you can also do evaluate somewhere from the menu, but yeah, everybody just presses Shift Enter. Yeah. Yeah. Good. Okay, let's move on. So today we'll have more fun. So this is only like the tip of the iceberg, right? So yeah. Good. So let's get back to where we ended last time. So keep in mind these numbers. So the triangular numbers and square numbers, they will be our heroes today as well. So good. Now today's topic is restricted partitions, right? So that's another condition on partitions. In this case, we will bound the number of parts that the partition have. Not bound, but exactly specify the number of parts. So here we look at integer partitions of n with, in this example, exactly 4 parts. So this is again our partitions of 7 that we just looked at. And then you see that only 3 of them have exactly 4 parts. All the others have either less or more. So I hope that's clear enough, right? So just restricted. So we'll be looking at this new function, new sequence p of n with a subscript k, right? So k fixes the number of parts. So here we see that the p3 of 7, p4, excuse me, p4 of 7 is equal to 3. Okay. I hope that's clear. Good. So now we're going to do another exercise. We'll look at a bunch of lists. Well, hopefully, I don't have to do it for too long. And then we'll make lists for say 4, 5, 6, and maybe beyond. And then we'll make a table of pk of n. So meaning that like for every n, we'll make a table. What is p1 of n, p2 of n, p3 of n, etc. So, and finally, pn of n. So we have here, right? So this is, for example, this is p. So pn of n consists of only this one, right? So p1 of n consists of only that one, and so on. So let's begin. Okay, I have a favorite picture. Okay, so now let's do maybe, well, some of the small numbers are. So yeah, so feel free to write the. Okay, maybe you can annotate. So let's say we start from here, right? So for n is equal to 5, right? So for n is equal to 5, what's p1 of 5, p2 of 5, etc. So make it for 5, and then maybe for 6, for 7, and then for 8. It's probably better to do it on your own, like not to clutter the screen, but you can annotate on the screen too. So, or we can just make a list. For example, for p5, you could make a list, right? So like sequence of pk's, so pk of 5, right? And then we'll put the numbers here, whichever way you like. So again, we're looking at so k in the index is the number of parts that a partition has. Yes. Right, so P1 of 5 is equal to 5. So this partition here, there's only one partition with one part. And that's probably the case for every other partition, right? So it's like the column partition. So let me erase that so you can have, yeah, I'll help you with the, so P1 of 2, so P3 of 5, P4, and then P5. And then let's just do different color for the 6. For 6, we have P1, P2, P3, P4, P5, P6, and so on with the 7. So, okay, so P4 is 1. Yeah, so P3 is 2. There are two partitions with 3, right? And then there is one with 4 and one with 5. Good. So we have, let me remove the duplicates. So you have 1, 2, 2, 1, 1, right? So let's add up together. So we have what? 7, right? So P of 5 is 7. So that's good. So that's the distribution. 1, 2, 2, 1, 1. For 6, we have 1, 3, 3, 2, 1, 1. Okay, maybe let's do 7 together, and then I have a table on the next screen. So just make sure that everybody on the same page. Okay, let's do that for the 7. There should be 7 of them, right? So P1, P2, P3, P4, P5, P6, P7. Let's get those numbers down, and then we can. So the idea is to see what's going on, like what's the. Well, we need to do some counting. Yeah, obviously there's some distribution, right? So it starts with 1, ends with 1, and there's some kind of shape here. We'll try to understand that. Okay, do we have the whole? It's 1, 3, 3, 1, 3. So that 3 belongs to what? To 4. So how many partitions with 4 parts? 1, 2. I would say 3. There are 3 partitions with 4 parts. Yes, and then with yeah. So with 4 there should be 3, and then with 5. It goes here. I apologize. Yeah, good. Right. Okay. Great. Right. So I thought that was easy enough. So now let's look at the table here. So I prepared a small table for you. So yeah, I hope it's self-explanatory, right? So here's K. In rows you have N, right? And in columns you have K, right? So clearly K should not be bigger than N, right? That's why it's lower triangular table. So our task now is to find some patterns here. Like just look at this first. Try to stare at this table, and see if you find anything, any patterns, any combinations of numbers that add up to some other number or something like that. So our goal. So let me tell what. So we're trying to understand this function p of n, how to predict the next p of n, knowing the previous previous p of n's, but not only for just for all partitions of n, but more specifically for restricted partitions. So say P3 of 6 is equal to 3, right? So P4 of 7 is equal to 3, and so on. So like kind of try to find, just tell me whatever you see here on this table, and well, let's try to find some kind of some patterns which would allow us to predict new numbers. So in other words, say we know the first 8 rows of the table, how to find the 9th row. We'll say we know the first 7 rows, can you find the 8th row using all the information above?
In column 3, it increases by 1, so it goes 1, 2, 3, 4, 5. So P of 9 would probably be like 6 in that next column.
1, 2, 3. So which was it? Where's 1, 2, 3, 4, 5? I only see
Right here. 1, 2, 3, 4, 5.
Okay, good. So you think there'll be six below that? But so is there anything special about k equals 3, right? Because there's now in other columns it doesn't work quite like that, right? So
Right.
it's 1, 2, 3, 5. It jumps here. But okay, that's interesting. So let's see once we calculate p of 9, we can see if this is a if your prediction will hold. Okay. What else?
For the second column, does it go by twos, like 1, 1, 2, 2, 3, 3, 4, 4, and so on?
Yeah, also interesting observation. Yeah, but again, so we should be able to check this once we calculate a bit more. Yeah, okay.
In every column, it starts with like a repetition of 1. So like in column 1, it's like all 1s, and then like there's always 2 1s in each column. I don't know if that makes sense.
Yeah, sure. Like to one, or like you could probably put like those diagonals, right? There's the 2 diagonals which consist of 1. In fact, good. So let's start with this. This should be easy to explain why this is the case. So look at these pictures. So and why do you think this observation with so 1, 1 means what? Means that there's always one part with a maximal number. So there's one part with maximal number of parts. So P4 of 4, P5 of 5, and there's always one part with 1 less than maximal number of parts. Why is that? Just by, can you tell it by looking at these diagrams? So where are these partitions? That Zeo just told us about, right? So the maximum, which partition gives you the maximal number of parts?
Because there is, if we just separate the number to multiple ones, we'll get the maximum number of parts. And if we just combine 2 ones together, it will be 2 plus 1 plus 1 plus 1 plus 1. So the number of that will also be 1.
That's right. Yeah. Or if you like, you can sort of visualize it like by moving blocks, right? So that's why we're doing this partition. So there's one part in every list with a 1, 1, 1, 1, 1, right? So clearly there's one of them, and then you take this block and you put it over here on the left, right? So, and you can clearly do it only one possible way, right? So there's only one way to move the rightmost block and put it on the leftmost position. So there's always one part of this kind, and there's always one part of that kind, like with a little hook with 2 1 1 1. And so there's single partition with 1 1 1s, and there's a single partition with 2 1 1 1s. So that explains these 2 1s in the diagonals. Okay. Okay, so that was easy, but it's kind of it's a first step. Okay, but okay, so maybe try to find the a pattern in the following way. So that let's try to add 2 numbers and then to get the third numbers. Is there anything anything like, you know, say for example 5 is equal to 3 plus 2, right? Or 4 is equal to 3 plus 1, or 2 plus 2. But we need to work this universally. So we need to find a rule. So remember I mentioned Fibonacci numbers, right? So it looks like Fibonacci numbers when you a sequence when you have each number is a sum of 2 preceding numbers, right? So it's 1, 1, 3, 5, 8, right, and so on. But here, can you try to find sort of the same kind of style of pattern? so that the number below is represented as a combination of numbers above.
Column 4 is the like the beginning of the Fibonacci sequence.
Good. What we've seen is right. So, but as we've seen it with the P of n, it only works till some moment, right? And then it breaks down. So yeah, again, so we'll check P of 9, but don't you think it'll be a bit too naive to assume that it will work? That's why it's only a few numbers. I mean, okay, so let's put it in the list to check once we get to P of 9. And try to work between columns, not only within each column. So yes, so as you say, so 5 is equal to 3 plus 2, but there's also 3 here, right? So or 5 is equal to 4 plus 1, 4 is here, 1 is there. Kind of try to kind of move it, think a bit broadly.
So I actually kind of looked ahead at this presentation because I wasn't entirely sure like what I had to do for homework.
But I thought
so
I only sent you I commented the other slides. I thought no. So you saw the follow-up slides or what?
I saw like the particular way that these connect.
Okay, so then maybe you can hold on. Maybe let other people figure it out. Yeah. So did you look at the proof? I thought I made those slides invisible. So did you see all the slides or what?
Yeah, I did see all of the slides. So it was, or at least I assume that's all of the slides. And I certainly saw like the particular proof for this section.
It's strange because I definitely skipped those slides when I printed the PDF. But okay, so let's think about. Okay, so do you know how to code? Can you write the code while others are thinking? They have like can write maybe in Python or C++ or whatever, which would calculate pk of n for the follow-up k. So that will be a part of the next homework. But if you have time, you can probably do it right now. So is that okay? So we can. So the rule which we're about to figure out will predict the following pk of n for higher k and n, right? So and it will be a recursive algorithm, right? So we go. So the answer would depend on the previous answer. So we can write a code, computer code or mathematical, any other way to, which will allow us to calculate pk ahead of us. So did anybody else look at slides? I was pretty sure I didn't print those skip slides, but okay, maybe you find some other file. Okay, so I'm glad that nobody else did. Otherwise, we would have had answers by now. Can you maybe give a hint to the others? So what's going on here? So where should they look? So give an example. So for example, this 5 over here. is there a way to decompose this 5 into a sum of something smaller? So 5 is 3 plus 2, or 5 is 4 plus 1, right? So you have some choices. So the idea, right? So see, there's a number here. We want to be able to predict it or to calculate it given the history, given the previous numbers, right? So we try to find out recursive formula like Fibonacci, only a little bit more complicated because we have two indices now, right? So so this 5 is 3 plus 2. This 5, well, let's see, it's like 3 plus 2, and this 5 is 4 plus 1, or maybe it's still 3 plus 2. So we need a rule that works for all the numbers, right? So kind of try to add two numbers on top. They should be somewhere on top in the table, which you combine them together to get the number from the bottom row, or to any row for that matter. Kyle, can you maybe annotate one example of those of the rule which you think will work? So 5 is 3 plus 2. So he takes 2. Good. So he takes 2 from the same column, right? So which means in the language of those partitions, right, is that we have P. So 5 is what? It's P3 of 8, and it is equal to this 2 here, which is P3 of 5 plus 3, which is P2 of 7. Of course, it's not the only way to represent 5. You could have tried 1 plus 4, right? Or take other 2 plus 3. But so see if you can sort of, what about this 5, right? So what do you think the most natural way to represent this 5 as a sum of numbers above? And try it with every other number, that you can do. 4 and 1, which one? Okay, so Venus wants this one. So this is what this is. Let's write it down. So it will be P4 of 8 is equal to this one, which is P4 of 4, P4 of 5. No, so 1. Okay, so we're gonna do it. Okay, let's keep it. So we have a choice here. So either this one or this one, right? So keep this. Yes.
I think is the one above.
This one, right? Okay, why is that? This one, right?
It's like it's forming a triangle, and the side of that column is actually, I mean it will form like a triangle.
Mm-hmm.
The triangle of the side just lies on that column is actually the you know, like this, the number on the first row. Like for
this side would be inside of the triangle.
For this one, 2 plus 3 equals 5. Like this side is 3.
Mm-hmm.
So, and for the row of 2, like we got 3 plus 1 equals 4, and for this side the length is 2, and
Mm-hmm.
and it's same. It's this applies to this all these rows. So maybe
yeah.
maybe it's.
let's see. So let's try it out. So I'm gonna circle, sort of let me erase the additional annotation here. So let's try to do the same color. So here, good. So this goes like this, okay. And then, yeah, so 4 is equal to 1 plus 3, which is equal to, yeah, so let's get by the comment with the side. So P4 is equal to P, so it's a P2 of 8, right, is equal to P2 of 6, right, plus P1 of 7. So as we just heard, like this side of this triangle, the number of boxes here is equal to the number k, right? So like this is 2, right, and then this is 3, and this is 4. Okay, what happens next? And then what happens next? Sort of this thing ends, right? So there's nothing here. There's a 0. So this 3 would presumably be just this 3, right? So there are, you know, there's 3 here, there's 3 there, right? And then there's 2 here and 2 there. Okay, and then there's 1, 1. So it kind of works diagonally, and then there's 1, 1. Okay, so now look at the formula above. See if you can come up with a general rule. So what pk of n should be equal to in terms of some other p's. There'll be 2 p's here. So you need to insert the argument and the index.
I think I see something with the numbers. So
Okay.
for all of the ones you wrote down, so P sub 3 of 8, you take 1 off the 3 and you get 2, and 1 off the 8 and you get 7. And then
So one of these means you need to put k minus 1 and minus 1.
yes. And
Good.
then the other one, I think you just subtract 8 minus 3 and you get 5 for the center number and you keep the base. So P sub k of k minus n.
The other k minus n is negative, n minus k.
N minus k, sorry.
N minus k. Good. Do you see it, guys? Right. Right. So pk of n. So you take the number, right? And then it is represented in terms of 2 parts, right? So first part is so as Emily just said, we take one. So there's this thing here. So when we go diagonally, right? We take 1k, take 1 n, which means we go top left, right? 1 position diagonally. So that gives us pk minus 1 and minus 1. And then the other one is in this the same column, k steps above. So that's pk of n minus k. See, so that looks simple enough. Now let's test it. So now let's sort of turn it around and see if we can test it for, okay, so p of 9. Yeah, so let's do the one in here, 10, 11, here, good. So okay, so let's, in interest of time, so let's assume that we also calculated p of 9. So this is the p of 9, right? P of 10, right? So this will be the same numbers. And now, yeah, so can we predict p11 using this rule? So please fill up the next row in this table using the rule that we just had. While either time could write it down, right? So it's pk of n is equal to pk n minus k plus p k minus 1 n minus 1. What do you, Kyle? Is this part new? So did you? I don't think there's a triangle in the diagram. Yeah, in the slides. So, yeah. Yeah, so part of the homework will be to make a code, to write a code which would do this calculation. Then you could compare with Mathematica, who is faster. Like in Mathematica, there's a function that returns the time it takes for to calculate. It's called timing. Okay, so we got some number. Let's sum them up. What's the total sum? So this is pk of n of 11. Can we calculate the sum? How much? So let's take sum pk of n, sum of all k from 1 to n.
6.
Sum of all these numbers. How much is this?
56.
56. Did you just do it? I mean, did you count it that fast, or did you look at the table?
No, I know the number of partitions of 11 is 56.
Yeah, that's what I'm trying. That was good. So if this is correct, it should be 56. Is it 56? Yeah. Check if this adds up to 56. No, there are people who calculate very fast, in their head. You can probably teach yourself to do it, but
Yes, it's 56.
Good. Great. So, okay, so it looks like it's working. So I think what now? Okay. So I think some of you said that this goes in groups of 2. So yeah, so that's also the case. That seems to be the case, right? So the Fibonacci thing clearly breaks down, right? So there's a 6 at P9. So you have 1, 1, 2, 3, 5, but then it's not 8 anymore, right? So Fibonacci didn't work, but the thing with the 2s does work, right? So we have always 2 partitions with, yeah. So okay, that might be that'll be one of, we can try to leave it at the homework, right? So okay, so it's going to be 6 here, yeah, right? To take this plus this, it's going to be 6, right? So you see here that the partitions go also in groups of 2 here. Okay, but what we're going to do now is to prove this formula. Okay, so it's a pattern. Again, it's not a proof. Maybe it breaks down on the next step, and then on the next step, and on the next step. So yeah, here's the table again. So 56 is the right number. Good. So here's again one of the examples from the table. P3 of 9 and P2. Yeah. So we're looking at partitions of 9 now. And so let's try to come up with an algorithm, with a recipe of how to map those partitions one to another. So here you see 7 partitions of 9 with 3 parts in green, and on the right you have 4 partitions of 8 with 2 parts and 3 partitions of 6 with 3 parts. So look at these pictures and see how you think we need to identify them. So we need to come up with a rule that maps, which we can sort of formulate in general for any k and any n. Did you do this part, Kyle, at home, or not yet?
Yes, this part was in the slides.
Yeah, but like, did you understand? Did you do it? Like, do I understand the rule? Or
yes, I do.
It's strange that only you saw those slides and everybody else didn't. So.
Okay, wait, let me try annotating something.
Yeah. So drawing will be easier.
If you like add 1 here, then that would be this one.
Mm-hmm.
And then if you do the same thing with,
should be from the same group, right? From the orange ones. Let's
right.
do this. Do all with the oranges.
So then like here, this, and then this would match to here. There.
Good. So right. So indeed. So that explains this. So that's kind of excuse me. No, the other one. It looks at this subset, right? So by adding this block to the bottom right, you add one block, so you increase n by 1, and you increase k by 1 because it's an extra part, right? So see here, these green partitions have 3 parts, orange partitions had 2 parts, but if you add those blocks like this, right, we will have we'll turn them into 3 parts. So just remind you, the part is just the number of blocks in each column, right? It's the height. Okay, so we have the match here. Much rather kind of embedding. So it shows you how to embed this for the set of pk and minus 1 into pk of n. So yeah, we need to show sort of the correspondence both ways, right? But it's kind of clear that it should work in both ways. Okay, so this is true. How about the rest? So what should we do about the other 3 partitions?
Can you add like 3 on the bottom like that for all 3 of them?
Yeah, let's see if it works. Yeah, let's draw it. Let's draw them. Yeah, so see if you do that, right? So again, you have a match. Yep, that's right. Good. So, and that kind of explains you this part of the correspondence, right? Because so you keep the same k, right? You keep the same k, so you don't change the number of parts, but you add. So you need to add k blocks to go from here to here. You need to add k blocks by keeping the same number of parts. What's the way to do it, right? You just add another row at the bottom, right? So that gives you exactly plus k here, plus k there, plus k there. So okay, so that's kind of mapped from right to left. It's mapped from the right hand side to the left hand side. Is that part clear? Some of you look confused. Do you need to explain this again, or is this okay with everybody? Good. Now let's do the dictionary from left to right. So what's the recipe? Say you are given a partition with k parts of n. Now, how do you decide which subset on the right will it belong to? So let me erase those arrows.
Wouldn't you just do the inverse? So you would take away a bottom column or subtract.
Row.
Yes.
Bottom row. Okay, so say you take away the bottom row. There's a little caveat. So yes, so say with here. So now I took away the bottom row here. Now, where should I send it? So you see, I take bottom row here. Now there's no diagram like this on the right. No, it has, this one has 4. It's 4 by 2 block, and this is 3 by 2. Or maybe I don't take the bottom row everywhere. Maybe there's a condition. So if I take the bottom row here, I get the one that I want, right? If I take the bottom row here, right, I take the one that I want. But if I take the bottom row there, and there, and there, then I'm in trouble, right? Is there maybe a condition on partitions where I should and where I should not take the bottom row?
When there's not a 1 in the parts, we just take the bottom row, and if there is 1 in the partitions, we take the rightmost column. Right.
So see, first we need to look at the partitions which have this block sticking out, right? So if the last part is equal to 1, right, then we don't take the bottom row. Then we just take this 1, right, or the last column. and we get our orange partitions, right? And if the last part is greater than 1, then we allow it to take the whole bottom row. And then we get the green partitions. So there is a condition. Because see, if you did just do it blindly, you'll get a bunch of partitions which do not belong to the other set. Yeah. Okay, questions here? Yeah, so see, it's an isomorphism, right? It goes, so we have constructed a one-to-one map between two sets, which works for every k and every n. Right, so now, as you can see, you can use this to find P of n, right? So, and it will be one of the homework problems. So say you have P of n, which of course is the sum. It's the sum of all restricted partitions of n. So you take the sum. So now you can calculate this using the recursive formula and using the table, right? So you only need a seed, like the initial conditions. You need to be if you look here, right, so you need to know only very few initial conditions. So say 2 is equal to 1 plus 1 and so on, right? So 2 is equal to 2 plus 1. So this is 2 plus 0, right? And then so 3 is equal to 2 plus 1 and so on. So you just need to start with very few. Maybe this triangle, you just define it into your even just the two of them. So you probably need to start with this triangle as your initial data. And then you feed it into your algorithm, and then it sort of generates. It generates you all the pKs, and then you just need to sum over all of them, right? And then you'll get the P of n. So it's one of the ways to calculate this sequence using the recurrent formula. Okay, is that clear? That will be one of the homework problems. I'll say it again in the. I'll send it to you more specifically, but yeah. So pick any programming language you're comfortable with. You can use Mathematica if you like. You can use Fortran or C++ or Python, anything which suits your needs. Yeah, and here's the summary, right? So that's how the correspondence work. So you would add a block, right? And then, yeah, so, and then, yes, I think we also forgot to specify this. So see, how do we decide which block to add? Well, I mean, it should have the right number of parts, right? So that was pretty clear. So we add a block here, we have k and n as less by 1. Okay, good. Any questions? Okay, moving on. So yeah, so let's try to understand. So there's another way to derive P of n, which uses a little bit more machinery. It is maybe some calculus even. So yeah, and we can start today. We have maybe like 25 minutes. Now, so well, here's another subset of partitions, which we will study. These are called. So we'll look at partitions with odd and even number of parts. So we're only looking at multiplicity, right? It's not multiplicity, at the number of parts. So say for each n we count distinct partitions. So only those which are distinct. So every part is different, and then every number is either even or odd. Every integer is either even or odd, right? So here, for example, for n equals 8, right? We have these 3 partitions in red, right, which have 1 and 3 parts. So these are odd guys, right? And those in blue are even. So those in blue, they have even number of distinct parts. Does that make sense? I know it's a mouthful, but it's kind of easy to show on the picture. So first, we impose 2 different conditions, right, on each partition. That its parts are distinct, and then we look at the parity, right? Either it's even or odd. Okay. So this is for n equals 8. This is for n equals 9. So we have 3 in each type, right? So we have 4 of them for 9, 4 of them with even number of parts, and 4 of them with odd number of parts, and 4 of them with even number of parts. I think I got my colors wrong, so odd should be painted in red, but I hope you got the idea. Okay, n equals 10. So we have we've got 5 and 5. N equals 11, we have 6 and 6. Now, what do you think will happen next? So do you think it will always be the case, or will it always be like, so there's a rule here. So in fact, yeah, so let's try to think before we proceed any further. You can pick your guesses. So here are some examples for n equals 10, n equals 11. So far, everything matches, right? The number of partitions in each category, in each list is the same. Can you come up with a rule? Like, so is there any easy way to map red partitions to blue partitions? You can annotate if you like. Yeah, so Emily, what are you doing? Like, what's the rule?
I took the one on the very right, the one that's on like last column, and then I brought that up all the way to the top.
Yeah, sure, that's right. So if it sticks out, you bring it on the top. Okay, let's continue. So what's next? Let's do the whole correspondence. Finish the list. So you can do this here. Yeah, I can do that there. So to get this one, excellent. Okay. I think there's one more where you can do that. Good. Okay. Now, what about the other two? What should you do?
So for the last one, I think you take the one on the very top, and then you bring that over to the bottom right.
And then here you throw it back down. So
yes.
That's right. Yeah. So that's how you get those ones. Right. And then see it like, yes, essentially, for some of them you need to do this. You need to move the block up, or for some of them you need to move it down, right? And so and then same thing, or you can do it in the green one, right? So in the blue one. So you say, if there's a block here, you move it up. There's a block here, you move it up, right? And then there's a block. So these guys, we move it up. These guys, we move it up. And then here we move it up, right? And then they correspond. Oops, is it right? Yeah, and then here, right? So, so yeah, sorry, this one. Yeah, this one corresponds to this one. This is to this one, to that one. Did I make a typo? Excuse me. Should be 11. 6, 5. No, that's fine. Yes, yeah. Thank you. You're right. Hold on, something's not right. That's 11. Yeah, and here you need to move 2, right? So here it's a bit, so you need to take, yeah, so when there are 2, it's a bit different, right? So you need to kind of map it, like 1 here. Yeah, so for this one, it's a bit more complicated. So you would take, yeah, so these would correspond, but you have to move 1 up on this row, 1 up on that row, right? So yeah, okay. So at some point it stops. Yeah, so it works, but you need to kind of, yes, essentially you have 2 of them here. You need to throw both of them in. So basically, see, the rule is that we have to, yeah, yes. So the so we see we have, this is 1 part. This is 3 parts, 3 parts, 3, 3, and 3, right? And then here we have 2, 2, 2, 2, 2, and 4. right? And then we'll always need to go down, right? So if you want to throw those blocks on the top, right? So say to go from 2 to 1, right? So 1 obviously is the smallest one, so you can go from 2 to 1. So we take the rightmost block and put it on top, right? And then from and now the other 2s have to come from 3s, right? So yeah, one of the 3s comes from 4, right? So we take fourth block, put it upstairs, and then that gives us one of the partitions of 3. And all the other 2s should come from 3s by taking the rightmost blocks and putting them on top, right? So this is how the rule works. So it works for 10, it works for 11. So for it should work also for this is the algorithm, right? So how it works for others. So 8, 10, 11, 8, 9, 10, right? So the rules are pretty straightforward. And here's 12. So try to match this with 12. Try to draw arrows. Let's see what's going on with 12. So how many reds, how many blues do we have? Do we have a match or not?
There's more reds than there are blues.
There's more reds than there are blues. Good. So let's find which of them stands out, which of them is exceptional.
Okay.
We can make a correspondence between all others. Yes, you can throw those blocks. Are you sure about this one? So yeah, that's right. So that goes. So see, it has 3 on here. So I would say this goes here. No. You would take the rightmost block. If you put it on top, you'll get this one, right? So get this one, and then if we do it, and then here, if you take the rightmost block here, you'll get this one. Yeah, you'll get that one, right? And then here, this one goes to this one by taking the rightmost block. Good. So the blue diagrams make only a subset of the red diagrams, and this one sticks out, right? So it has. So what is so special about this diagram? So why you cannot do any manipulation with blocks as we did with the others, right? So what's wrong about it? So what does it have that others don't?
Does it have like a square?
Good. So it has a square, right? Excellent. In fact, yeah. So I'm glad that you noticed it. Yeah. So it has a square. Indeed, it has a square, and some little triangle on top, right? So let's keep it in mind like this. So remember, I told you in the beginning to keep an eye on triangular and square numbers, right? So in fact, this is a sum of the square. In this case, is 9, and then the triangle is 3, right? So there are. This partition, you can sort of break it down into 9 plus 3. So 9 is the 3 by 3 square, and 3 is just this triangle number on top of it. yeah. So and none of the other partitions have a square, right? So so now indeed, so if you try to do any manipulation with so see. Let's try to understand a bit better why it's a special partition. So let's recall what those guys are, right? So these are the guys in the blue are what? So remember, all of the partitions must be distinct. So all of them are distinct, right? Now, what happens if you take this block, move it up here, down there? If you try to. Will we compromise this distinct property?
Yes.
Right, exactly, because then the first two columns will have the same number of blocks, right? So see, so we cannot move it down there. Simply because, yeah, so that will break things down. So in fact, because there's this diagonal over here, there's not much we can do without spoiling this distinction property, right? So any manipulation, any sort of movement of those cubes within our rules will spoil this, will break the, will not the partition will cease to be distinct. So in a sense, it looks like an isolated case. Yeah, and then also, yeah, so also you cannot. So that's one thing you cannot do. So and then also the yeah. So I mean, you could you could move say this block here and then these two blocks on top, right? But it's not going to be it's not the rule that we're doing, right? So we want to try to find a universal rule which would work in this case. So yeah, so this one is special, and then you can ask yourselves, what about other numbers? Like which others are special? So turns out that these are so-called pentagonal partitions. You can think of them as pentagons. So as Eunice said correctly, they all have they look like pentagon. Well, maybe the way they're drawn, they're not exactly pentagon, but you can arrange them in sort of, they would kind of look like a pentagon. And they come in two different series. So see on the bottom, you have, so the pentagon in, you can only count black dots, and you can only count black dots with the white dots on the bottom. So there are two kind of pentagons, which in terms of partitions work like this, right? You would take, say here, there's one square. So see, there are two pentagons with the same number of parts. So there are two, so with two parts, you have 5 and 7 over here, right? And then with 3 parts, you have 12 and 15, and so on. So with 4 parts, you have 22 and 26. With 3 parts, you have, with 4 parts, you have 22 and 26. With 5 parts, you have 35 and 40, and so on and so forth, right? And with the 1 part, you have 1 and 2. So there are 2 series of pentagon numbers, which we'll talk about next. Now, as you can see, all of these partitions over here, they have this property that you cannot do the simple manipulation with blocks, right? So you're not allowed to take this block and put it down, because otherwise the partition will stop being distinct. Or equivalently, you cannot move anything up, which will follow the rule that we have formulated. So you can see that there's a sequence of infinite sequence of partitions which break down the rule. Right, so this will be very important in calculating the function p of n later. Okay, so here's the table. So that's another time for exercises for patterns. Now, what is what here? So Tn are triangular numbers, Sn are square numbers, and Pn are pentagon numbers. So one with the corresponding n, right? And here is just all integers, including negative integers. So n goes from minus infinity to plus infinity. There is a 0, and there are zeros everywhere. So let's try to find patterns in this table now. What do you see? Tell me what do you see, and we'll put down those formulae. You can
the
edit.
SN,
Yeah, go ahead.
the SNs are squares.
Yeah, SNs,
and
right. So, okay, that sort of goes without saying, right? So SNs are number of blocks in square of size n by n, right? So yeah, so of course they're all squares. Yeah, there's no doubt about it. Yeah, so these are all squares, and the triangle means that it looks like the staircase partition, right? So this is T3, and this is S1, 2, 3, 4, 5, right? This is S5. S5 is 25, right? T3 is equal to 6.
I saw that the pentagonal number on the bottom was equal to the square number directly above and the triangular number 1 to the left.
Good. So if you add this together, you get 3 plus 9 is 12, 10 plus 25 is 35, and then here, if for the negative numbers, 10 plus 16 is 26, 28 plus 49 is 37. Good. So we can write it like this in this case, that Sn plus Tn minus 1 is equal to Pn. Right. Okay. What else?
Well, I think the Tn numbers, they increase by 1, 2, 3, 4, 5, 6, 7, like this sequence.
Sorry,
So
I guess
can I annotate?
Yeah, absolutely.
Yeah. So from this to this, they increase by 1, and by 2 here, by 3
okay, good.
here.
Yeah, good. Right. So that's yeah. So that's the pattern within triangular numbers themselves, indeed. So, so to get from say 6, you do it's 3 plus the counting number 3, right? Then to get, for example, 21 is 15 plus 6. To get 36 is 28 plus 8, and so on, right? So that works like this. So Tn is equal to Tn minus 1 plus n. Yeah, and that's not surprising because you just add one row on the bottom, right? And you get T4, right? So you get as many as before. Excellent. Good. So that's that. So remember, we try to find, yeah, so that's, yeah. So PNs, and so one of, right. Let's see what else do we have.
And we have T negative n equals T n minus 1.
T negative n. Say 10, okay, what is it equal? So 10 is T negative 5. What do I want to do with this?
And T negative n equals T n minus 1.
Sorry, yeah. So Tn minus 1, right? So 10 is equal to, yeah, so right. So T minus 5 is equal to T4. Yeah, precisely. Good. Yeah, so it's a T minus 7 is equal to T6, right? So there's almost a mirror symmetry because it's kind of slightly asymmetric. There's a shift. Yeah, good. But so there's a shift by 1 because there's a 0. It's because T negative 1 is also 0. So there's like a reflection symmetry relative to this line over here.
And the same thing with the square numbers for S of negative n equals S of n.
Yes, that's right. Only here there's a reflection around 0, right? So it's kind of reflection over here. Yes. Okay. Good. So now how about P with negative n? Is there any connection between P with negative indices and P's with positive indices and something else?
There's like T negative n equals negative, no negative, I mean P negative n equals P n and add by n.
That's right. Good. So indeed. So I think that should be enough for us. So we have say 57 is equal to 51 plus 7, right? So maybe n plus 1, right? So n, so n minus 1 probably here, right? So n, sorry. Like this, like this. Oh, plus n plus 1, excuse me. Yeah, plus n plus 1. Like this, right? Oh, no, what I'm doing, plus n, sorry, plus n, yeah, of course, yeah, plus n is I apologize, yes. I added incorrectly. Plus 6, good, yeah, that's right. And then also, yeah, so for example, 26 is equal to 22 plus 4. Good. I think that's best. So we have these two rules, and of course, like you can use these relations to combine, and they'll have other patterns. There are many of those, but anyhow, so see, so we have two sequences, if you like, or like one sequence with sort of this. We can think of them as sort of two sequences in one. So we have sequence of pn's and p negative n's, right? And then they differ by n, right? So if can you explain why this happens using the pictures? So see that, yeah. So can somebody explain in terms of Young diagrams this rule over here? That to get p with negative n, we get. Let me show you pictures back. They have pictures here. Yeah, maybe here. So now we're going to denote them with this double index, right? So there's a pn and p negative n, and this is what we assign them for. So see, we have p1 and p minus 1. It goes. So the series that we had before, it has. We'll assign it to these diagrams. So index in the pentagonal number will coincide with the number of parts, and you can see there'll be two pentagon diagrams for each k, right? Because we can add. Essentially, there are two pentagons that we can make for each k, right? So there's always a square k by k, right? Only now the for the p with the negative index, we just add an extra row, right? So it's like you take in, if you like, you can take a square and then you try two different triangular numbers, right? So the one with the k minus 1, so you can also write it like this, right? So that p, yeah. So as we said, so p k is equal to sk, right, plus t k minus 1, right? And then p negative with index minus k is equal to sk plus tk. And as we discussed before, these two guys are different by k. Okay, excellent, good. So there'll be so this will be the sequence of pentagonal numbers. Okay, so another simple exercise for home will be show this simple formula, right? That you can use maybe induction or any method you like. Show that these pentagonal numbers, they follow this pattern, right? And then so I'll send you maybe some more homework to do, and then for the next time we'll use this fact to count partitions of n. So there'll be some calculation. So there'll be more. It will be more sort of formally heavy based for the next time. Okay, so any questions here?
So what's the homework assigned?
Yeah, so first problem will be to write the code which calculates p of n using the using this partition, using the this formula. So what, to calculate p of n, all right, so yes, first is to calculate p of n. Yes, pk of n. Okay, goes 1 from n. So you need to code this, write the code, and then do the well, and calculate it as high as you can. So for example, what will be p of 200? So you do the calculation and tell me what P of 200 is. And second will be prove the formula for triangular numbers, right? So for the pentagon numbers, so the Pn is equal to, what is it, n times 3n plus 1 over 2. And maybe I'll send you some more. So sort of, okay. Does it sound good? We can begin with this and then see how it goes. So next time we'll start with understanding this formula better from the point of view of pentagonal numbers. So pentagonal numbers will be crucial in deriving that formula. Okay, great. Then that's it for today, guys. See you next week. Thank you. Bye.
Thank you very much.
Thank
See you.
you. Bye.
Thank you.
Thank you. Goodbye.